Greetings, everybody. Learning is a hobby. Here with your problem of the day. Let me bring up the problem and we'll get to it. Um, so this is going to be a Fourier series problem, which I want to give you guys sort of an introduction here to Fourier series because maybe at some point in the future I can do some fun things with Fourier series on the problem of the day. So we're going to do a Fourier expansion for a simple function here today. So let me read out the problem. Find the Fourier series for f of x equals x, where x is between negative pi and pi, and extend that piece to have period 2 pi, and then we'll find the Fourier series expansion for it. Just so you can see what it looks like, this is the graph of the function that I'm talking about. So it's y equals x over the interval from negative pi to pi. So you get that line segment, and then we just extend it to have period 2 pi. So it just repeats itself every 2 pi radians, you know, as you go through over the entire real line. All right, so it has some discontinuities here. Notice that at each odd interval, each odd integer multiple of pi, you get a jump discontinuity. All right, so that blue graph is the function that we're going to do. We need some facts here that I'm not going to have time to prove in this video, so I'm going to leave it to you guys to prove it yourself. These integrals are not that difficult. These are Calc 2 level integrals, I guess, or even Calc 1 integrals if you're you learned integration by parts in Calc 1. So you learn integration by parts either in Calc 1 or Calc 2, depending on your college. These are the three integrals here. Let me read them out for you, and then we'll use them to derive the Fourier series. So the integral of sine mx times cosine nx dx, where we integrate over the symmetric interval negative pi to pi, is always 0 for all mn. Here I'm assuming that m and n are integers for each of these facts. All right, so that integral is always 0. Fact number 2, if you integrate sine mx times sine nx dx over the same interval, you get 0 if m is not n, and you get pi if m is equal to n. And then 3, a similar type of integral to number 2, except we have cosines here. The integral of cosine mx, cosine nx dx over the interval from negative pi to pi is 0 if m is not n, and pi if m is n. So, like I said, you can prove these easily on your own if you know how to do integrals. Excuse me. I'll give you a hint here in case you want to try to prove these yourself. You can either use the sum or some end difference identities. You'll have to use both identities for sine and cosine, or if you don't want to do that, you can just use integration by parts. All right. The integration by parts here involves a little bit of a trick, but it's a standard trick that you learn in single variable calculus. So, like I said, I'll leave that to you guys to try if you want something fun to do. If you have a few minutes. So we're going to use those facts to derive the coefficients for the Fourier series. So let's say we have a general function f, a real valued function, so a function from R to R. Then there are, under certain conditions, there are a series A sub n, which will be the coefficients that we have here in the Fourier series, which I'll read out in a second, and bn. The an's go from 0 to infinity, and bn goes from 1 to infinity, such that f of x is equal to a0 plus summation n going from 1 to infinity, an cosine nx plus bn sine nx. This is called the Fourier series expansion. And notice that I don't have an actual equal sign here. And that's because the equality here can be a little bit tricky. I don't want to get into too many details in a problem of the day video, but it turns out for a function that we are looking at to a function like the one that we're looking at today that has jump discontinuities like the one that I showed you, the function is equal to its Fourier series almost everywhere except at the points where the jump discontinuity happens. The Fourier series actually converges to the average of the upper and lower points on the curve. I'll show you that in a second, but that's why I have this squiggle here um, instead of an actual equality. Um, now, uh, not every function has a Fourier series expansion, but again, I'm not going to go into the details here. The function that we're looking at today does have a Fourier series expansion. So if the function f has a Fourier expansion, it looks like that. All right, so let's derive the formula for finding the coefficients a0, an, and bn, because once you have those, then you know the Fourier expansion. Okay, so to find the ANs, what we do is we integrate both sides of this equation here with respect to sine mx. Sorry, did I find the ANs? Well, the first one I did was the BNs. You integrate both sides of the equation here against sine mx, over the interval from negative pi to pi. Um, and then when you do that, uh, this integral here will be zero because sine mx is an odd function and we're integrating over a symmetric interval. And then all of the integral of all the sine mx times sine nx's will go to zero over that symmetric interval due to the facts that I showed you up above, except for the one where the coefficient of x is the same. So you only end up with the bm integral negative pi to pi sine squared mx dx. And when you integrate this from the facts up above, you end up with bm times pi. And I can divide both sides of this equation here by pi, and that gives me the coefficients for the bm. All right, I can do a similar thing to find the coefficients a sub m, where m is greater than or equal to 1. Again, you integrate both sides of the equation here against cosine mx, where we integrate over negative pi to pi. And when we do that, again, this integral goes to 0. And then all the integrals of cosine mx times cosine nx go to 0 by the facts up above, except for the one where n is equal to m, and that gives you this integral, which is the only one that survives, and it's equal to pi. So again, we get pi am equals this integral, and we can solve for a sub m by dividing by pi, and that gives us a formula for the AMs. And lastly, to find the A0, again, you integrate both sides of the equation of the Fourier series with respect to over the interval from negative pi to pi, and then you end up with 2 pi a0 when you do that, because the only integral that survives is this one. All of these end up going to 0, and then you just divide by 2 pi, and that gives you a0 equals this formula here. So now we know how to find the coefficients for the Fourier series for a function. And we want to do that here for f of x equals x. Before I do that, let me just make a note here. If you watched my video yesterday, I said that the set of even functions and odd functions were orthogonal, in a certain sense. You can think of I don't know how far I should go into this because I don't want this video to get too long, but the set U, E, and U, O are orthogonal, for example, with respect to inner product. Let's say we go from negative pi to pi, fg dx. This is equal to 0 when f even, g odd. So this is the sense in which it doesn't necessarily have to be this integral itself, but just should suggest in what sense I meant yesterday that the even and odd functions are orthogonal to each other. If you don't know what an inner product is, or you don't know integrals, don't worry about it. I just wanted to mention that. And also just another relationship here between what we're doing today and what I did yesterday. Notice that the function f here, I have written in terms of an even function. And let's do purple maybe. And an odd function. The summation applies to both of the terms here, but the summation of the bn s sine nx gives you an odd function. So uh, just to call back to what I did yesterday in the problem of the day, if you watched it. Okay. Anyway, let's get back to what we were doing today. I want to find the Fourier expansion for f of x equals x for all x between negative pi and pi. Uh, I should probably say continued with period 2 pi. All right, and we can just use our formulas that I showed you up above to find the coefficients. So if I want to find the ANs, I can integrate uh, integrate both. I did both of these together. Integrate to find a0. This would give you a0, but notice that this integral is 0, and this would give you the AMs. But notice that they're all 0 here for both of these. This is 0 because you're integrating an odd function over a symmetric interval, and here same thing. You're integrating an odd function over a symmetric integral. So both of these integrals go to 0. So AN is 0 for all n greater than or equal to 0. All right, and then the BMs you can find again by just using the formula up above. So we take the integral 1 over pi, integral negative pi to pi, x sine mx dx. And in order to do this, you have to use integration by parts. So that's what I'm doing here. And then when you do the integration by parts, you end up with this answer here, negative 1 over m cosine m pi minus 1 over m cosine m pi. And just a fact that I maybe should have mentioned up above, cosine m pi is equal to minus 1 to the m for m, an integer. Just a fact that may not be obvious. So when I simplify this, I end up with 2 over m times minus 1 to the m plus 1. And then plugging that into the Fourier series expansion, we get this Fourier series here for the function x. So you get summation n going from 1 to infinity, 2 over n, negative 1 to the n plus 1, sine nx. And if you graphed this Fourier series, like I said, it would look like the blue curve here, except at the jump discontinuities, the Fourier series would converge to the average of the height here and the height here, for example. So you end up with just a single point on the x-axis at all the jump discontinuities. So it's almost equal to this function here, except at the points that are at a odd integer multiple of pi. And just to convince you that this does actually happen, I just wanted to show you the graph of this Fourier series on Desmos. Right now, Desmos won't graph the actual Fourier series for you because it doesn't let you take a sum where the upper limit is infinite. But you can let the upper limit get bigger and bigger, and it should show you what the behavior happens as the series, the terms in the partial sum, get larger and larger. So, for example, here I have that Fourier approximation, I guess you could say it here, where the upper limit is 5. If you graph that one, which is just a partial sum, it's not the actual Fourier series, the graph of the actual Fourier series, notice that you get this function that kind of looks like that function y equals x. It's not so great, but it's kind of looks like it. But we can make the top limit of integration bigger. For example, if I let it be 10, the approximation looks even better. If I let the top limit of integration equal 100, it looks even better. And maybe I'll do one more example. If I let it equal 1,000, notice that it looks even better. And as the upper bound, the upper limit of integration, of summation gets larger and larger, the two graphs will look more and more like each other. And like I said, it'll converge to the graph that I drew on the whiteboard a few minutes ago. This is called a sawtooth function for hopefully obvious reasons. It kind of looks like a saw blade. So that's what the Fourier series looks like if you, well, if you graph the partial sums anyway. The actual Fourier series, like I said, if you graphed it, would look like that. Okay, so like I said, I wanted to do a Fourier series expansion problem for you guys here just to introduce you to it so that maybe we can do some fun things with Fourier series later on down the line in the problems of the day. So let me stop my screen share. Let me know what you guys think down below as usual, and I'll see you guys tomorrow again with something interesting.